This flow chart will continue though into chapter 11, so I'll keep referring to it. That's on page 95 of the reader. And then you'll see in the reader on page 96 and 97, I'm not going to cover it, but there's some advanced ways to do Lewis structures which are actually faster than the way I showed you. And in OChem you will probably use this method, but we typically don't cover it here. But if you want to learn it, you can do your Lewis structures a little faster. If you have questions on it, you can ask an officer. We're going on to chapter 10. It's bonding part 2. The last chapter is bonding part 1. And we're not going to do it in order. And I'm going to do section 1, then I'll jump to section 5, and then I'll go back to section 2 later. Some parts of this chapter you might not want to read if you don't want to freak out, and that would be section 5. Okay? It's actually not a hard section, but again, like chapter 7, the first time you see it, it's weird, and then after you get used to it, it's pretty easy as far as the problems go. Okay, so section 1. So kind of what happens in section 1 is we go over the problems with Lewis. And that's described in your reader and in the text. I'll just kind of say them verbally. Lewis doesn't work well with metals, especially transition metals. It doesn't always work. You'll notice we've mostly avoided transition metals on purpose. Okay? You have to take pretty advanced classes to figure out how that works, and there's some different rules that work with metals. The nice thing about Lewis is it's easy to draw, but it has no quantitative or numerical results. So I'm not calculating anything. I don't have, oh, this is a bond energy for Lewis. So that's another problem. Another problem with Lewis, it doesn't deal well with the odd electron species, which they exist. And so what do we do with the odd electron species? So what's going to happen in this chapter, we're going to look at a different theory in section 5. I'll describe that there. Okay, that is a little more helpful than Lewis. It's not as easy to draw, but it can give us more results that are numerical. All right. Now, what you might not have realized is I never told you what a bond was. So I want to tell you what a bond is now. I'm going to use this graph and I'm going to draw on top of it. Okay? So as you kind of follow along, you can draw with me. What's a bond? A bond has multiple parts, actually. So what's the first part? Well, as two atoms fly together, in this case we're talking about these two atoms form H2+, and this is actually the data for H2+. As they fly together, there's going to be some attraction that forms the bond. So this is some positive, low energy, good attraction. Okay? And low energy, if you didn't realize, is good. Okay? We don't want to expend, in general, high amounts of energy to expend. We wouldn't want to do that. That's why we like to be lazy. So low energy is a good thing. And as two atoms fly together, I'm going to illustrate by this line right there. They have a bonding interaction. And more technically, that happens because orbitals, remember chapter 7, orbitals overlap. When orbitals overlap, that can be good because there is constructive interference. Constructive interference is favorable. It causes two orbitals to overlap and add. So it's additive. You might vaguely remember this from chapter 7. That term, constructive interference. So that, as they fly closer and closer together, so this x-axis is r, or the distance between the two atoms. The closer they get, the more favorable the bonding interaction, thus going lower and lower energy, which is the y-axis. Okay, there is also another force in play for two atoms. When two atoms start to get closer and closer together, their nuclei, which is made up of protons and neutrons, but protons, most interesting for us right now, as those get closer to closer, they start to repel each other. There's a repulsive force because you can't get so many protons right on top of each other. So there's this repulsive force that is this line right here. It goes higher and higher energy. This line right here. Higher and higher energy because the repulsion between the nuclei. And this is called anti-bonding. Okay, remember this is actual data for this molecule. Anti-bonding, we might describe it another way, destructive interference. Destructive interference. When you add those two factors together, you get this middle line here, right here. It's not that linear actually. It looks something like this. Highlighted again in green, but I'll write it brown here. This is called the sum curve. It's literally the sum of the bonding plus the anti-bonding. So we call this sum curve. When you add these two other curves together. Now, see this line, this dashed line right here, that dashed line. Notice this distance from the dashed line down to the bottom here. We call this the well, or the lowest part of the sum curve. The lowest part on that y-axis of the sum curve. This is the bond energy. So we can actually calculate the bond energy. It's just that little dip, or the part of the well there. That's how we know what the bond energy is. That's the bond energy. And then this distance from here out to the well, again, lowest part on the y-axis, this is the bond length. Because that low energy spot is the most favorable spot for those two atoms to sit, where it's fighting against the bonding positive action and anti-bonding negative interaction. And so that is the sweet spot right there at the well, and that's how we know what the bond length will be and the bond energy. And that's what a bond is. The key concept for you is every bond has two parts, a bonding part and an anti-bonding part. Okay? And you're going to see that come into play as soon as we start section 5. Every bond has two parts, a bonding and an anti-bonding part. Okay? Both of those pieces make up one bond. Alright, I'm ready to move on if there's no questions. I can show you a picture from your textbook. They try to make the sum curve a little more beautiful. And this is not actual data, just the artistic rendering. But here's the well. And this distance here would be the bonded length. And this distance, top to bottom here, would be the bond energy. Okay? This is for H2. So this is the sum curve. They're not showing you the bonding and the anti-bonding curves. But that's from your text. You can take a look at that if you want. Okay, section 5. Let's use that information to do MO, or molecular orbital theory. Section 5. So remember, we're going out of order. We skip from section 1 to section 5. Okay. You remember the s orbital, there's p orbitals. There's actually 3 p orbitals. They go different directions, x, y, and z. Now I'll actually show the 3 different directions. There's d orbitals. All these orbitals here, there's 2 things I want to show you about these. These are, we call them orbitals, which they are, but more specifically, I'm going to put an adjective on the front. These are atomic orbitals. Orbitals for atoms. So everything we did in the chapter 7, those were atomic orbitals. What we're going to deal with is a molecular orbital theory, and there's orbitals for molecules that look different than this. Okay? We're going to draw those molecular orbitals. They're atomic orbitals that combine to form molecules. That's it. One thing we have to add into the picture that I sort of avoided so far is the phase. And the people have asked me about that, and now is where it becomes important. S orbital is one particular phase, but a p orbital, the top is out of phase with the bottom, or the left is out of phase with the right, or the front's out of phase with the back. And anyways, one lobe is out of phase with the other, and you can show that in two ways. You can put a plus sign in one and a minus in another, which is what the book often does. Or you can do it the way I'm going to do it in class. One side is shaded, and the other side is unshaded. And that shows they're out of phase. It's a similar, it's when mathematical functions are out of phase, or like the moon, full moon, half moon, no moon, etc. That's out of phase. The moon's out of phase. So this is mathematically, those sides of the lobes are out of phase. For a d orbital, two lobes are shaded, the other two are unshaded, to show the phase again. Okay, so shade is one phase, unshade is another phase. These are atomic orbitals. I'm going to show you how to make molecular orbitals. So let's try that. And then we're going to use this theory to make molecules, simple molecules for our class. We're not going to do any math, but you can use this to do math. And people who do theoretical modeling, if you want to be a chemist and you're into programming and theory, not really into the lab, some people do all their research on a computer and they use this theory. Okay? So the theory we're using is the top theory that people use today, molecular orbital theory. Let me show you how to make some molecular orbitals. Let's take two s orbitals and add them. Two s orbitals, and we'll make them one s orbitals. A 1s plus a 1s just makes, all you would do is draw the two orbitals next to each other to bond. Now really, it would be a big blob. But if I see that, I don't know if you've just drawn an s orbital or a blob or what the heck that is. So I want you to draw this if you have to draw it. Okay. Now, we call this, let's do this in black here. Here's the center of this one, here's the center of this one. See how the overlap or the bond occurs between the center points? So thus we call this a sigma bond. Sigma bond, because the bond occurs between the center points. And we subscript this with a 1s to remind ourselves this sigma bond came from 1s orbitals. Okay. You could also have a 1s orbital add to an out of phase 1s orbital. Okay. So I'll shade one and leave the other unshaded. They're both out of phase with each other. Zoom in a little bit. So in this case, you get this. Okay. Just draw the circles right next to each other. Notice the bond occurs between the center points of the two atoms, or the two orbitals. And so we still call this a sigma bond. It's still from a 1s, but I'm going to put a star here to signify they're out of phase. Or the top one is bonding, the bottom one is anti-bonding. The top one is bonding because they're same phase, constructive interference. The bottom one is anti-bonding, meaning they're out of phase. A shade and an unshade are touching. Okay? So they're out of phase, and so we put this little star, and that means anti-bonding. Okay? These would subtract from each other. You can see the pictures in the text if you want. But basically, the whole middle part would subtract and be left with a little tiny unshaded blob and a little tiny shaded blob on the outskirts. And there'd be void space in the middle. You don't have to draw this again on the bottom parts. I'm just showing you what I want you to draw or know about is the top one. Again, the left-hand side is atomic orbitals, the right-hand side is molecular orbitals. I would want you to be familiar with this part here and this part here. Okay, let's try another one. Let's try a p orbital. Here's a 2p. Here's another 2p. I'm adding 2 atomic orbitals. I'm about to make a molecular orbital. I'm just, oh, that was it. Right here. There we go. I just dropped those 2 atomic orbitals right next to each other. And now this forms actually a different kind of bond. Notice the center points are here and here. These 2 points are the center, but the overlap or the bond occurs above and below. When that occurs, we don't call it a sigma bond anymore. There's no overlap in the middle. We call this a pi bond. And it comes from a 2p, so we subscripted 2p. And maybe you'll see the pattern. Sigma is what letter? S, and pi is p. Thus, that's where it comes from. The sigma comes from overlapping s orbitals, usually, not always. And the p will usually come from overlapping pi orbitals, or p orbitals. Pi. If you're Greek, you're really jiving with this right now. Okay, let's try another one. Another 2p with another 2p. But let's put them out of phase with each other. So now, again, draw them right next to each other. They're flying in to bond with each other. But now they're out of phase. Notice again, the bond is not happening via the center. It's happening above and below. So again, I'll call this a pi. It comes from 2p orbitals. Well, what else do you think I'm going to add? Yeah, a little star right there. Because just like at the very top, very nice, you all. Just like at the very top, when a shade hits an unshade, we call that anti-bonding. And so, this is going to be antibody or destructive interference. They're going to subtract each other. Okay, let's try one more. This is a tricky one, the last one. I'm going to put 2 p orbitals together, 2 2p's again, but I'm going to put them at this orientation. So let me have them fly in together to bond, like that. What do you think this is, a sigma or a pi? Yeah, even though they're p orbitals, here's an example where p orbitals make a sigma bond. The bond occurs through the midpoint. It's from a 2p, so I want to subscript the 2p. And I'm not going to put a star because the same phases are overlapping. 2 unshaded phases are overlapping. This is a sigma 2p bonding molecular orbital. You'll see I have similar pictures in the reader on page 100. The textbook kind of has similar pictures, but they're so artistic, you wouldn't be able to repeat them. Okay, what do I do with this information? Now, you know how we draw Lewis structures, right? We're going to draw the equivalent, but now with molecular orbitals. So we're going to draw what's called a molecular orbital diagram. But don't worry, we're going to do the easiest possible one first. H2. This is an H, bonding to the H. I've already drawn the Lewis structure. There it is. Now how this is going to work is and this is going to take me about a half a page. The center part of the diagram is going to be the molecular part. And then on the outsides, I'm going to imagine the atoms are flying in to make the molecule. So the outsides will be the atoms, and they're going to fly in. The middle part will be the molecule. It's going to look weird at first until you realize, oh, it's always the same. Okay? This is the first time you've seen it, it'll look more strange. I'm going to put the H's on the outside that are going to fly in to make the H2. And I'm going to write the electron configuration. 1s1, and for this one as well, 1s1. And then I'm going to make on a y-axis an energy diagram, like that. Energy axis. And I'm going to put randomly the 2 hydrogens. I'm going to draw a horizontal line for both of them. and that represents their energy level. And since they're both the same atom, they're both at the same energy. And this is a 1s orbital, and this is a 1s orbital energy. Okay? Now let's draw those orbitals. They're spheres. They look like that. We already know what a 1s orbital looks like. Every bond has how many parts? 2. The bonding and antibond. Okay? They're about to form a bond, so we're expecting now 2 parts. The lower energy one is bonding, higher energy is antibond. So we're expecting a low energy part and a high energy part. They're gonna, let's beautify this. The beautification is these dots. Look how much more beautiful it looks when I put the dots there. Wow, I feel good. Okay? I gotta stop looking directly at it. Okay, now, when they overlap in the same phase, that's the bonding interaction. Is this a sigma or a pi? Sigma. What do I subscript this with? 1s, because it came with from a 1s orbital. And then when it overlaps opposite, out of phase, like that, sigma or pi bond? It's a sigma. What's a subscript? Again, 1s, but what's the difference? Put a star for antibonding. Every bond has 2 parts. The bonding goes lower energy, the antibonding goes higher energy. And that's what it would look like on an energy diagram. The only thing left is to put in the electrons. Let me put that in a different color. Each 1s orbital has 1 electron. It's a 1s1. 1s1. Total of 1 electron from each side. So the molecule will have 2 electrons. So start filling them in. 1, 2. Done. This is a molecular orbital diagram for H2. This would be the equivalent of drawing a Lewis structure for H2. Okay? But I showed you the energy. Let's try another one. If there's no questions, maybe you're too stunned. You're like a deer that just got hit by a car. Try another one. I want to draw H2 minus. Oh, there's a question, yes? Oh, why didn't the electrons go up here? Well, they would rather be a lower energy. Lower energy is always more favorable. Think of college students. Would you rather be lazy and watch YouTube or study for chemistry? Obviously. It's an obvious answer which one is lower energy. I'll let you think about that. Okay. Let's do H2 minus. This is a molecule that has an odd number of electrons, and we could not draw this with Lewis. So there's no Lewis structure equivalent here. So this is where MO theory becomes more superior. We're going to do the same thing. Draw the energy axis. And part of the question that was just asked about why they don't go to antibonding will be answered here. Okay? This is a 1s1. How about H minus? It's 1s2. There's 2 electrons. It's like a helium. Okay? So let's draw this. We've got 2 hydrogens here. They're going to make a bonding and an antibonding. Let's beautify this. Oh my gosh. Don't start lusting, everybody. That's beautiful. Okay? Now, I want to draw the 1s orbitals. They're going to be in the same phase on the bottom and the opposite phase on the top. The bottom is called a sigma 1s, and the top is a sigma 1s star. What's the difference between what I have right now and what I did before? Pretty much nothing. Okay, you should see that these 2 pictures are so far identical. Do you see how they're so far identical? That's why this is going to get easy, because the pictures will look the same. Okay? Now, what the only difference is the number of electrons. Here there's 1, and now here there's 2, for a total of 3. One from one side and two from the other side. So let's fill these in. Now, those of you who had a question about where the electrons go, it's time to watch me before you do it. 1, 2, now this is filled. Go up here to the antibonding. 3. Okay. The only difference is the number of electrons. Now, let's drink a little bit of the Kool-Aid right now. Which one, top or bottom, is diamagnetic? Top or bottom, which one's diamagnetic? The top is, because in the top everything's paired. What's the bottom one called? Paramagnetic. Which one would essentially be a magnetic, top or bottom? Bottom. Typically, when we have you draw out one of these molecular orbital diagrams, we'll ask you about the magnetism. That's a normal question. Okay, there's one more question we'll ask you, and that is the bond order. What we just learned, but now there's some mathematics to it. So those of you who prefer mathematics, you'll be happy right now. The bond order is actually calculated in these pictures. It's the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. Okay? That's how you calculate it with MO diagrams. Let's do the bottom one first. The bond order for the bottom one is, let's do the top one first, in fact. Let's do the top one. Bond order is, you're going to divide by the number 2. It's number in bonding molecular orbitals, that's this number right here, or 2, here, 2 electrons, minus the number in anti-bonding molecular orbitals, 0. So you get the number 1. And that means what kind of bond? A single bond. 1 means single bond, and that's what we expect from Lewis. So you got a single bond, that's exactly what we expect. Now in the bottom picture, we don't have a Lewis diagram equivalent, so we just got to calculate it. How many electrons in bonding molecular orbitals? 2, that's this number, minus 1 from an anti-bonding molecular orbital electron. So we get 1/2. This has a half a bond. Is that shorter or longer than a single bond? It's longer. Remember, the shorter the bond order, the smaller the bond order, the longer the length. Is a half bond have more or less energy than a single bond? Less energy. Okay? See how that all connects from what we just did? Okay. Last one. Helium-2. Again, you cannot do this with Lewis, it won't work. We'll do more next time if you're wondering, oh no, is he going to stop? We're not going to do any more molecular orbitals, don't worry. We'll do more. So 1s2 for the configuration of helium. They're both 1s orbitals, but now there's 2 electrons in each 1s orbital instead of 1. Each brings 2. And remember, every bond has 2 parts, the bonding and the anti-bonding. You don't even need to draw the circles actually, and you'll see in the textbook sometimes they don't. This is a sigma 1s, and this is a sigma 1s star, just like before. Just like before. The diagram is identical. The only difference is the number of electrons. So the template's always going to be the same. Okay, let's fill in those electrons. There's 4 total, 2 from each side. 1, 2, up here, 3, and then 4. Okay? Is this para or diamagnetic? not experience a magnetic field. It's diamagnetic. Let's do the bond order. Number of electrons in bonding molecular orbitals, how many? 2. This number right there, 2. Minus 2 from 2 right here. So this means, what kind of bond is that? It's not a bond. Does helium-2 exist? No. Here's why. All right, that's a good place to end.